Welcome to this video. In this video we're going to talk about complex differentiation, i.e. differentiation in complex analysis. Now this is the first part of complex analysis that is truly exciting because differentiation here is truly going to be different to the way that you differentiate in vector analysis. Specifically, we have throughout the playlist on complex analysis stressed the similarities between complex functions and functions from R2 to R2. Now, in functions from R2 to R2, you often perform partial derivatives, directional derivatives of each of the components of those functions. The type of derivative that we are now going to introduce for complex functions is different in an amazing new way to partial derivatives and directional derivatives, and it will take you a little bit of getting used to, because partial derivatives and directional derivatives, it's very easy to understand what those mean. You can visualize what those mean, especially when we're just dealing with functions from R2 to R2. You can imagine each of the components, if you like, as being a three-dimensional graph above the R2 plane that's representing the domain, and then you can think of the partial derivatives and the directional derivatives as representing a gradient of that three-dimensional graph. Whereas what we're about to introduce in complex analysis, which is complex differentiation, is much more difficult to interpret what it means visually. So let's go for it then. So as always, let's have a function f, which is a complex function, so from C to C. Let's now define how to differentiate this function. So I'm just going to draw the picture because we need the picture. We'll need it in a moment. So here we are. Here is the domain. Here is the codomain, and we'll be studying some point in the domain, which is z0, which is being mapped onto f of z0 by the function f. So what then does it mean to differentiate the function at the point z0? This is what it means. It means take the quotient function, as we always do when we're differentiating, take the function f, add on an amount, little h, subtract off what the value was at z0, and then divide that by h. So this is a very familiar term from real analysis and vector analysis. So what are we doing? We're going to our point z0, we're looking at what does the function equal at z0, and then we're going to another little point a little bit forward from that, z0 plus h. We're working out what does the function equal at z0 plus h, and then we're taking the difference between those two, the difference in the codomain, and then we're subtracting that by the difference between the 2 points in the domain, which is h. The strange thing here is, what is h? Because before, in real analysis, it was obvious what h was. It was just a real number, some positive real number, or you could have even seen it as a negative real number, but it was a real number. In partial derivatives, again, it was obvious what h was. It was either an increment in the x variable or an increment in the y variable, or if it was a directional derivative, it was a incremental vector in the direction that you're taking the directional derivative in. But now, I've not told you a direction here. H is just any tiny little complex number. So if I want to put it on here, h could be this tiny little complex number that's going to translate us that far to take us to the new point. So this is z0. H then is taking us to the new point, which is z0 plus h. We're then working out what is f of z0 plus h, which is over here. We're working out what is the difference between f at z0 and f at z0 plus h, that complex number in blue that produces that translation that I've drawn as a little arrow here, and then we're dividing that, taking the ratio between that and the original complex number here, h, which is, that's common sense for what to do for a derivative. The difficult bit is, what is this h? What direction is this h going to be in? Well, we're not going to specify the direction. Instead, it could go in any direction, and that is the new complicated thing, because this is truly going to be a derivative in 2 dimensions rather than a derivative in 1 dimension, which is what you have always done in vector analysis previously. When you have taken partial derivatives and directional derivatives, you might have thought, oh, isn't this fancy, I'm working in higher dimensions than 1, but actually you've always reduced it back down fundamentally to working with functions in 1 dimension and then just using normal real analysis to differentiate, always. Whereas what we're about to introduce is a truly 2-dimensional derivative. So let's see how we're going to do this. So if we set our point where we want to take the derivative, and we have set our point, we're going to take z0, we could in principle construct this function here. And let me show you what I mean by that. What we can imagine doing is letting h, and I should have used red rather than blue, so I'll go to red here. So we could imagine this is now another complex plane, another function, we're setting up another function, and this is going to be the h variable. So you can let h equal any of the complex numbers in the complex plane bar 1. You cannot let it equal 0. So we're going to exclude 0 from this little operation, because of course if you let it equal 0, you end up with something totally meaningless. You end up with f of z0 minus f of z0, which is of course 0, and then you end up trying to divide 0 by 0, which is not algebraically defined. Indeed, you can't, the division, remember, algebraically is multiplying by the multiplicative inverse. There is not a multiplicative inverse for 0 in the complex numbers. There is never a multiplicative inverse for 0 in a field. It's not defined. It's just a stupid idea to try and do that. If you try and define a multiplicative inverse for 0, as I've explained in previous videos, it ends up breaking the other rules of field theory. Distributivity breaks, and distributivity is far more important to algebra than having a multiplicative inverse for 0, so don't bother trying to create a symbol for the multiplicative inverse for 0 and adding it on to the set of complex numbers. You end up with something that is utterly rubbish and doesn't warrant study. So we're going to have this function defined for all values except 0. So this is the complex plane that is h. We can let h take any of the complex numbers except 0, and then we can work out what this value is. We've set our z0, so then we can put in h here. We can let h vary over all of these. We can work out what is f of z0 plus h. We can then subtract it from f of z0, which is of course just a constant, and then we divide it by h to get some complex number, and then we can plot that as a function. So this one I'll have in blue here. Oh no, that's not what I wanted. That's the highlighter rather than the pen. So over here we can have our codomain, and every value of h is going to be mapped onto some value in the codomain, and that value that it's going to be mapped onto is given by this function here, this quotient that we've created here. So we can imagine creating this. You can do this, and you can do it for every single z0. It's a big job, of course, because every single z0 is going to need a separate one of these functions created. So if you went to a different z0, if you went to, let's say, z1 over here, then what you'd have to do is create a whole nother one of these. You'd have to put in z1 here instead, and then you'd end up with a whole different function for that point. And again, it would be a whole function of the complex plane without 0 onto the complex plane. So you could create one of these functions for every single point on the complex plane. We'll go back to our point z0 for now. So we've created this function mapping h onto the complex numbers that's defined on the entire complex plane except 0, and this function is specific to the point z0. What we can then do is, we know that this function is not defined for h is equal to 0, but what we can ask is, maybe there is a limit of this function as we get closer and closer to z0. And of course this is exactly what we do with real derivatives. We say let h get smaller and smaller to 0, let's take the limit as h approaches 0, except that now we're not just taking a limit in one direction, we're going to take a complex limit, which remember is a limit in all directions. So we're going to ask, does this limit exist in the complex sense? So we're going to take the complex limit, not a real limit, which is what we've always done in partial derivatives and directional derivatives. You've always taken a limit along one dimension. We're now going to do the limits in complex analysis where we take limits in 2 dimensions. So we're going to take the limit as h approaches 0, so we're taking the limit of this function here as h approaches 0, and h of course is the domain of the function. And we're going to ask, does that exist in the complex sense? So as you approach this point from every single direction, do we approach one value? And remember, in order for that limit to exist, it can't just approach a certain value from one direction and then approach a different value from another direction. It has to approach the same value from every single direction. So that is a big requirement. And if that limit does exist, then we have a good value, and we will call that value the derivative of the function f at that point z0. And then you have to do this, or imagine doing this, for every single point on the complex plane. So you have to change z0 to z1 and then do it for every other point, and then try and work out, does this limit exist for each of them? And if it does, then you can work out what the derivative is for every single point of the complex plane. So this is how we define the derivative. And of course it looks exactly the same as how we define the derivative in real analysis, except that we have changed the x to z here, or rather I should say that that is the derivative at f of z0. That's the derivative evaluated at z0, but we could change the z0 to a general z, and then that would be the derivative of the function at a general point z. So it looks exactly the same as the one from real analysis, but remember the difference is that the one from real analysis is looking at a one-dimensional limit. It's looking at going along a one-dimensional line and seeing if we come from both directions, does it approach a certain limit, whereas we're now looking at coming from all these directions and seeing if it approaches a certain limit. And let me just explicitly contrast this to what you do in vector analysis. So let's say for a moment that we have a function f which is mapping R2 onto R2, and let's just make this explicit. Let's say that we have our 2 components in the domain, which we'll call x and y, and the 2 components in the codomain we'll call u and v. So u is a function of x and y, and v is a function of x and y. This describes our function. If we want to draw a picture of this, one of the very simple ways that we can do it, or one of the nicely intuitive ways, the engineering maths way, is to imagine a 3-dimensional graph, like so, and then we can plot each one of these functions, each one of these components, as a 3-dimensional graph. So we can imagine plotting u of xy here. So just to make this clear, the plane that I'm colouring in red here is the domain, that's the x and y, so this is the x-axis and this is the y-axis, and then we've got we're imagining plotting one of our variables, which is just a real number, as a function or above our xy plane, which is our domain. This is a nice visual way of viewing a component of the vector function here. So I'm just going to get rid of the red lines because it's difficult then to draw an actual picture. So this is the x-axis, this is the y-axis. So then we can imagine having some sort of graph like so. So it might look something like that. And then when we differentiate this function, we do a partial derivative, and what that looks at is it says we'll add a tiny little amount to the, if we take the partial derivative in the x direction, we'll add a tiny little amount to the x component, and we'll measure the difference in the u function, and we'll divide that difference by how much we changed the x variable. So what that is effectively doing, and we'll take the limit as h approaches 0. So what that is effectively doing is it's going to a point, and let's say we're going to a point here in our domain, our 2-dimensional plane, and then it's saying the value of the function is this, go forward some way along the x-axis or in the x direction on this line that goes through a point in the domain, and that's supposed to be a point not on the surface that I've drawn here, but a point in the plane, the xy plane below, whereas this point here is supposed to be its value on the surface, i.e. its u value. So we're saying go along that line, which is effectively what we're doing when we alter x by an amount h. You're moving the point along this line that's parallel to the x-axis, and you could then imagine, equivalently to what I've said here, you can imagine creating this function where the function varies in h, but h is only a real variable now. It's only a one-dimensional variable. It's not a two-dimensional variable. So you can imagine, if you like, we could create a function down here. This is a real line. This is a real line. Here's 0. Here's 0. And this is our variable h this time. It's only varying in one dimension because we're only changing it along this line. So this line is effectively similar to this line. As we alter h along here, we're moving along that parallel line here. And then you could plot the value of this function that we've created here, which is just a real number. After all, u was a real number. It wasn't a vector, it was a component of a vector, so just a real number. So we'd end up with a function which is r to r, and then we're taking the limit of that function as h approaches 0. So effectively it's just reduced down to single variable calculus, real analysis. Even though you think you're doing multivariable, you think you're doing vector analysis and you think this is all fancy, actually all you ever do when you differentiate is reduce down to working with lots of components, but each one of those is reduced down to a real valued function of a real variable, so you're back down to single variable calculus, and the limits are all one-dimensional limits rather than two-dimensional. And equivalently, when you take the partial derivative in the direction of y, again, you're just altering it along a line. You're only producing an alteration along a line that is parallel with the y-axis, and you're taking a limit along that line parallel with the y-axis. So when you take this partial derivative with respect to x, you're asking, does a limit exist as you approach 0, as you approach a change of 0, but you're only approaching from this side. You're only approaching from this side and from this side. You're asking, does the limit exist as you approach this way and this way? You're not asking, does it exist as you approach all directions? So it is just a one-dimensional limit. And even when you do a directional derivative, that's a little bit more computationally tricky because you don't just go in line with the x or the y-axis. Instead, you just pick a random direction, a direction of a vector. Again, it's still just a one-dimensional limit. You're asking, does the limit exist as you approach from both sides along this line, not from all directions in the two-dimensional plane. So partial derivatives and directional derivatives are very different to what we are asking about here with complex differentiation. Because they were one-dimensional, this is asking about two-dimensional limits, and therefore it's a much bigger ask. It is a much bigger ask. For a function to be complex differentiable at a point is a much bigger ask of a function than for you to be able to construct partial derivatives or directional derivatives. So far fewer functions are going to be complex differentiable, and that's what we're going to study in complex analysis. These incredible functions from a two-dimensional plane to a two-dimensional plane that are complex differentiable, i.e. they have this amazing property that when you take the limit of this quotient from all directions, it exists. So, I hope that some of that has gone in for you. This is a difficult concept to get used to because you have spent potentially your entire mathematical career dealing with one-dimensional derivatives, whereas now I am suddenly introducing this concept of two-dimensional derivatives. Do not underestimate this. It looks as though it's perfectly intuitive, perfectly sensible, but this is a massive new leap forward, the idea of it needing to approach something from all directions. So, if this value exists for the point z0, then we say that the function is complex differentiable at the point z0. If it exists for all elements of the complex plane, then we would just say that the function is complex differentiable. Let's do a few examples, or a example at least. Well, let's do a few. Again, we'll go to our most basic functions, and the beautiful thing about this is that all of the results, a lot of the results, are so beautifully in line with the results in real analysis or calculus. So let's just take some examples. So if we have a function f of z and it's equal to just z plus some complex number, some fixed complex number that I'll call a. So a doesn't need to be a real number, it doesn't need to be a sole imaginary number, it could be a mixture of complex and real and imaginary parts, it's just some complex number. If I was to try and differentiate that, how would I do it? Well, I'd have to imagine adding on a little complex number h to it, in which case I get z plus h plus a. I'd then take away the value of the function at z, so I'd take away z plus a, and then I'd divide this by h, and I would take the limit as h approaches 0. Now, of course, z plus a cancels with z plus a, so I just get h at the top. I get divide by h. Remember, h is never equal to 0. We're taking the limit as h approaches 0, but h is never equal to 0, so h divided by h is just going to equal 1, and therefore the limit as h approaches 0 is just going to equal 1. So this sort of a function, you would just get that the derivative, so the derivative, which we call f prime of z, just like in calculus, would be equal to 1, exactly analogous to what the derivative of x plus a constant value is in calculus. You can also write this as df dz. Whoops, I was about to write df dx. df dz, that's another piece of notation that you can use for the derivative of a complex function. So that was an easy example. Let's now take a slightly more complicated example. F of z is equal to 2 times z, or we could have gone more complicated. In fact, maybe we should. Let's just have a constant a times z. So if we wanted to differentiate that, again, we have to imagine adding a small value, little h, which is some small complex number, to our value z. Then we subtract off what it was prior to adding the h, and then divide by h. Again, you can just multiply that out, so az will cancel with az, you'll get a times h on the top. The h's will cancel because, again, remember we're taking the limit as h approaches 0, but h never is equal to 0, so we then just get the constant a. So look, this is all looking quite beautiful, isn't it? F prime of z is going to equal a. Completely analogous to what you'd see in normal calculus. And in fact, what we're going to see is that all the polynomials, they differentiate. If you take a polynomial in real calculus and take its equivalent polynomial in complex calculus, all the derivatives are exactly the same as they were in real calculus. So let's just do one more example of this. So f of z, let's say, is equal to z squared, my favourite example. So if we were to try and differentiate this, again, we'd have to imagine adding on a small complex number h, we'd square it, we'd then subtract off z squared and divide it by h, and then multiplying that out, we get z squared plus 2zh plus h squared minus z squared over h. And that will come out as 2z, again because the h will cancel. Well, I'll go through this fully. The z squareds obviously cancel off. The h would cancel here, so we get 2z, and then we get 2z plus h. And what is the limit of that as h approaches 0? Well, h is just going to get smaller and smaller and smaller. From whatever side you come, it gets smaller and smaller and approaches 0. 2z is constant because it's not changing as far as the h is concerned. Of course, z is a variable as far as the complex function was concerned, but as far as this process, which is the process for working out the derivative, is concerned, h is the variable, and z is a fixed value. So that doesn't vary as h varies. So therefore the derivative of this, so f prime of z, is going to come out as 2z. And indeed, for all the other polynomials, higher polynomials, it all works out exactly analogous to how it would work out in real calculus. And the reason for that is that what we have just done, all of these algebraic manipulations and all of these notions and taking the limit, it's exactly analogous to how you work out the derivatives of polynomials in real calculus, and therefore the derivatives of the complex equivalents of these polynomials are exactly the same as the real equivalents. So, thank you for watching this video. That was a basic introduction to the notion of differentiation in complex analysis. We will study this more and more and more. By the way, the chain rule and the product rule from real calculus, they also apply in complex calculus for complex differentiation. And the reason is exactly analogous to what we've just seen with polynomials. The reason is that the way that you would prove the chain rule and the product rule in real calculus, all of the same arguments can be used in complex calculus, and therefore you end up with these same rules holding true. So the chain rule and the product rule hold true. The quotient rule then comes from the chain and product rule, so it also holds true. So the chain and product rule, quotient rule, are true in complex differentiation just as much as they are for real differentiation. Thank you for watching.